Have you ever wondered how these amazing self-driving cars build a 3D representation of the scene? When they drive around with just a bunch of sensors like cameras, they can really build a three-dimensional representation and a map of the world around them. With this map, they know where the other objects are, they know where they are with respect to these objects, so they can perform obstacle avoidance while staying on course to get to your destination as soon as possible and as safely as possible. So the heart of this entire mapping structure is called bundle adjustment. Without bundle adjustment, you would not be able to reconstruct a map of that of a scale of a city, let alone that of like multiple cities when you're doing that intercity road trip, right? Let's dive right in. So in the past few videos, which I highly urge you to watch, we have seen that given a bunch of input images, in this particular case, this could be sequential images from a self-driving car. Or if it's images taken for architectural monitoring, they could be taken by different surveyors and we would want to align them to get a 3D representation of the world. So in the first set, we pick two random images. They could be the first two, they could be any random two, as long as there are matches, that's a good call, right? We take these two images and we estimate in the first step the fundamental matrix using the 8-point algorithm and ransack. Then we utilize this to estimate the essential matrix. Then we basically do linear triangulation to obtain the poses, and in which we get 4 camera poses by disambiguate, and we want to disambiguate them to obtain the correct pose which corresponds to the point of the camera in the world with respect to 2 images. And then we refine this point cloud using nonlinear triangulation, and then we start bringing in new images. We bring in the third image, and which we perform linear PNP with ransack, which basically lets us put this image points of the third in the map of the first 2 frames, so that we are aligning the map now, and this lets us estimate the scale and we align it perfectly. And once that is done, we basically do a nonlinear PNP to refine it even further. If it's a small sequence, like a few frames, we can get away by basically just doing this and repeating this step over and over again. But if you want to really deploy this on a robot, like for self-driving cars or like architectural monitoring, this is not accurate enough. And as you make a loop in the real world, the loop will be an open loop in this reconstruction because the ends don't perfectly align. So what we have to do instead is now we estimate something called the visibility matrix and then perform something called the bundle adjustment. The reason it's called bundle adjustment is because you are adjusting the camera poses along with the 3-dimensional structure or the point cloud you have estimated to perfectly fit to minimize the overall error. And once you do that, this would look perfectly amazing, something like this. In this video, we are going to deep dive into bundle adjustment and really dive into the math and the understanding of why we need it and how we can actually perform this. Just like we did in the nonlinear triangulation case and nonlinear PNP case, we formulated the initial problem as a linear set, and then we said that it's actually a nonlinear problem, so we really have to do a better nonlinear adjustment. Bundle adjustment is basically taking this nonlinear least squares to a whole different level. It's basically nonlinear least squares on steroids, right? The idea is that you have some function f of x equal to b, where f is a nonlinear function. What we want to do is we basically want to minimize this function fx minus b square is equal to, and then set it closer to 0. So if we do a plot of error versus x, where x is the variable we are trying to estimate and e is the error we are trying to minimize, in this particular case it's defined as the L2 square of the difference between fx and b. So let's plot one exemplar function. It might look something like this. And we want to find this optimal value or the minimum value where the function value is minimum. We'll call that x star. Of course, looking at the plot, we know that to estimate this from Calculus 101, we can differentiate this function e with respect to x, set it to 0, and we will obtain the solution as x equal to x star. But the catch is that this function being non-convex, you can have other points which are also basically going to give you the derivative to be 0. And these are shown by x hash. And these are local minima, which are not as good as the global minima, but they are solutions to this problem. So there are mathematical ways to deal with it, and bundle adjustment way is one way, hopefully, that we obtain the global solution and not really these local solutions. So let's take this error function and basically let's split it out with linear algebra. It's going to look like fx minus b transpose into fx minus b. If we expand it out, it's fx transpose into fx minus 2fx transpose b plus b transpose b. So to obtain the ideal solution, or the minimum solution, we already saw that we need to differentiate this with respect to x. So let's take partial e with respect to partial x and we differentiate this entire function. This partial f by partial x is basically the one highlighted in yellow, is called the Jacobian matrix. The Jacobian matrix is like the matrix equivalent of derivative which you see in scalars. So let's look at this Jacobian matrix into more detail and see what it actually physically represents. So Jacobians are at the heart of the optimization problem we are going to solve. So we essentially want to minimize the geometric error. The geometric error egeom is defined as follows. We basically have a point which we detect through SIFT, and in this particular case it's x, and the Captain Marvel is looking at this point of that world point which is detected by the SIFT feature. And depending on our estimate of the world point, we can also back project it into the image plane. And in an ideal world, this x hat, the projection or the reprojection, is going to line up exactly with the point x. But because we have noise and our estimations are not perfect, x hat will be close to x if it's a good estimate, x hat will be really far away if it's a bad estimate. Our goal is to minimize this distance between x hat and x in the simple Euclidean norm distance. We know that from the pinhole equation, we have like these points through the pinhole projection equation, where here red things are basically the unknown quantities and black things are the one which are known or given from previous approximation step. So let's try to minimize this geometric error. We know that x hat is obtained through the projection matrix. So it's going to be like the projection of the x element divided by the z element and y element divided by the z element for the y part. So we know that these yellow parts are what we are trying to estimate and the green parts are what we have from our SIFT detection. Let's look at the first step. In the first step, we are going to look at what is called the point Jacobian. The point Jacobian is basically if the world point has some error or it's twiddling around, how does that affect the geometric error? Because what happens is as x is noisy, your x hat is going to be noisy. Though your x remains in the same spot, your x hat is going to be different because of the capital X world point being different. And if it's a really bad estimate, it can be really off. So we want to basically quantify this quantity in terms of error and see how changing this capital X essentially changes the error variable, e-geometric. So this is where we had left off. We basically said we want to minimize this geometric error, and this is where we were. And what we are trying to do is we are trying to twiddle around this capital X in all directions. So this is going to be delta X, and we want to essentially see how that varies the error. So the function f of both the image point and the world point is given as follows through the projection equation, where we are just normalizing these values x hat and z hat and y hat and z hat. Remember that the hat represents the reprojection. To obtain the derivative, it's simple. We just apply the chain rule for the fractional terms, and this is what we get. Let's look at what the value of dx hat by d capital X is and so on. So to obtain that is what the point Jacobian represents, and we are basically going to apply the simple chain rule, and this is the answer we get. And the geometric error is going to be minimized for two different views, here Captain Marvel and Iron Man, and it could also be done for multiple views like n views. And in this particular case, we are just taking a simple L2 average of each of the views. And remember that the update rule for us is updating delta X to minimize the error. It's going to look something like this. This is the standard gradient descent where we have the partial f by partial x as given by the equation on the top. So if you're using a Levenberg-Marquardt optimizer, basically we just add another term, which is basically an extra damping factor to stabilize the training if it's actually very noisy. The error between the point and the camera pose are cross-coupled. So in this case, we saw the error due to the world point, but we can also have the error due to the camera pose estimation. Let's look at that as well. So the camera pose estimation can be like really off from the actual thing. So the world point, when we put it back, will actually be really off, right? And the farther the camera view is from the original, the worse it is going to look for our geometric error, right? And we have our standard pinhole equation and we have our geometric error defined this way. And what we want to do now is we want to twiddle around the camera position through delta C, and we want to see how this actually affects the error for us. So what we want to essentially do is we want to see the partial of the reprojection point with respect to the camera coordinates, and this is what it's going to look like. If we actually like solve this, this is what the equations will look like. But the catch here is that we generally do not represent the rotation as a rotation matrix, because we found that using a quaternion is much better numerically. It's a lot more stable and it renders to optimization much better. So what we can do now is we want to find this partial of this entire thing with respect to the quaternion Q. So we are just going to apply the chain rule. So we are going to utilize the partial rotation matrix with respect to the quaternion, which is called the quaternion Jacobian, which is a prefixed quantity which we can pre-compute. And given the quaternion is represented as the scalar and then xyz, this is exactly what the rotation matrix is in terms of the quaternion. So the partial r with respect to partial q is going to look like that. In this particular case, it's a 9x4 matrix because we basically vectorize the rotation matrix, which is 3x3 into a 9x1 vector, so that we get something like this. So this is great. And what we can do now is we can utilize this Jacobian of the rotation matrix with respect to the quaternion and find the Jacobian with respect to the geometric error with respect to the rotation quaternion. So let's first define the pose of the camera as the translation vector C and the quaternion Q. So it's a 3 plus 4 of 7 parameters in total. So when we try to get the partial of the reprojection point with respect to the pose, this is what it's going to look like. Right? So it's going to be split between the translation and the rotation part. Remember that the Jacobian for the reprojection was basically obtained through the chain rule of fractions, and we have done that before. So let's quickly recap. We basically have our geometric error. We basically have a camera point, which is going to be projected onto the world point, and the world point will be reprojected back onto the camera point. There is error in both the camera location and the world point, and they're cross-coupled to each other. By twiddling around both the camera pose and the world point X, which we can see there are two Jacobians we obtain. So given the reprojection error is given as the function of camera point or pose P and the world point capital X, we basically obtain, by applying chain rule twice, the partial with respect to the camera pose and the partial with respect to the world point. And this is what it looks like. And to obtain the solutions to these, we already saw the camera and point Jacobian. The Jacobians are going to look like this. And when we start putting this giant Jacobian matrix together, in this particular case, this is for camera pose J and point I. We have a combination for every single point and camera pose as long as they see each other. If they do not see that, that will be a 0 value. For each of these boxes here, we have 2 rows. And so if we bring, this is for a simple 1 point and 1 camera pose case. If we bring in the second point and the second camera case, this is what it's going to look like. And you see that this matrix is huge and it grows as a square of the number of points and the number of camera poses. So this matrix can get really big really fast. Let's look at a simple example to illustrate this. But the first question is, how do we make repeatable and robust features? I wanted to pause the video for a second and think about this. So the one way to do this is make patterns that are easy to identify and distinguish. Remember that we have these like things around in the world. I want you to pause this video for a second and think about where you would have these unique patterns which actually has information embedded in them. Hint that you use your smartphone to take pictures of this and basically use it for something really cool. The answer is very simple, something like QR codes. We built something called fiducial markers in robotics. QR codes are just a special example where information is embedded, and fiducial markers do the same thing. And there are multiple ways to construct these fiducial markers, which are very robust to recognize and detect and can have information embedded in them. In these particular cases, they have like this thing called the tag ID, which enables you to distinguish one tag from another one. Let's say we go around the room and stick a bunch of these guys, and we basically point our camera and look at this, and we want to estimate where these tags are relative to each other and estimate the camera pose of where the camera was with respect to each of these tags. And that's what we will reconstruct with this stuff we are going to talk about right now. In our simple example, let's say we have 4 tags with different tag IDs, let's say 0 to 4, and we have 3 different camera poses. We have moved the camera, right? And we'll call these points as P1, P2, P3, P4, and we'll call the camera poses as C1, C2, C3, and they're color coded so you can follow along where each of these points are going. So let's say in the first camera view, you see all the 4 tags. In the second camera view, you see all the 4 tags. And in the third camera view, you see all the 4 tags as well. When you write your Jacobian matrix, this is what it's going to look like. It has a beautiful structure to it, where the first 3 columns represent the camera poses, and basically the last 4 columns represent the 4 points. It's always going to be camera first, all the camera poses first, and all the points at the end, right? So here the number of unknowns is basically 3 into 7 plus 4 into 3, which is 33. And the number of projections we have is we counting the number of rays, it's basically 3 into 4, which is 12. What could happen is when you're moving your camera around, the image could be blurry, or something could happen to the tag which is occluded and you might not see it. In this particular example, camera 1 does not see the point 4, camera 2 does not see the point 3, and camera 3 does not see the point 1. In which case, these rows which are grayed out will basically become zeros for us. The rows will exist, but they will just have zeros all around. So the number of unknowns was still 33, but the number of projections is only 9, it's not 12, because some points were not seen by the cameras. In this particular case, there were 3 missing. Remember that when we are trying to do the gradient descent gradient update, the gradient descent update is going to look like this, where J is the Jacobian matrix, right? This Jacobian matrix is pretty huge, and we are trying to obtain this J transpose J and inverse of that, which essentially makes this the main bottleneck. In this particular example, for just 4 points and 3 camera positions, the size of J transpose J is 24 by 24, which is huge, right? Now you can imagine if you're trying to put this on a self-driving car, you have millions of points in a city level thing, and you basically have thousands of camera positions because each car basically is operating at 30 frames per second. And if you have even 10 minutes of video, that's thousands of frames, right? So the question is, how do we make this work in real time? Because we cannot invert like a million by million matrix, right, on a computer. It does not fit on the RAM, and it will be too slow even if we had a supercomputer in the background running all this stuff for us. So let's look at how this matrix looks like for a larger example. This is what the J matrix would look like. And here, just to give you perspective, anything that is white is basically 0. Anything that is has a color is basically some value, right? And the first set of these things is basically the camera positions, and it's a few thousands like we discussed. And we will call this part of the Jacobian as the JP, which represents the Jacobian of the camera pose, right? And the remaining part is for the 3D world points. This we are going to call this the Jacobian JX, and we are going to color code it as blue and yellow respectively. And J is made up of the Jacobian for camera pose and the Jacobian for 3D world points. Note that J here is sparse. Sparse here means that out of the total number of values which are non-zero in J, they are actually a very small percentage, right? And we can basically utilize this trick. So when we take J transpose J, it's going to be a square matrix. Because J was sparse, J transpose J is also sparse, right? If we sort of zoom into this initial part, this is what it's going to look like. Beautiful. If we just look at that first part, that is going to be this matrix, which is going to be the cross coupling between the Jacobian of the camera pose with itself, right? And then we have the diagonal elements, which are going to be the cross coupling between the Jacobian of the camera pose and the world point. And the D part is the last part, which is going to be the Jacobian of the point with respect to itself. So if we sort of color code this entire matrix as follows and write it out like this, we can do some really cool mathematical tricks. Remember that our update equation is something like this. This is basically the gradient, which we are going to use in gradient descent through the learning rate. In our particular case, we have two of these gradients. We have the gradient due to the camera pose, dp, and we have the gradient due to the world point location, capital X, right? Because our function f is a function of the world point, capital X, and the camera pose, small p. So if we multiply J transpose J on both sides, this is what we are going to look. It's going to look like. Since we know that J transpose J can be split into both the point and the camera pose position like this, and we can write the equation in this way. Let's call this as epsilon p and epsilon x for the error in the camera pose and the error in the world point, capital X, right? And if we were to try to do this in like a Levenberg-Marquardt sort of way, where we need it to be numerically stable, because J transpose J might not be very stable, we can add just a simple mu into the identity matrix to make this more stable with a damping factor. Okay, let's get back. And this is of the form of A, B, B transpose and D. And this is a perfect form for us to make this optimization better. So if we take this thing and multiply it with this matrix on the left hand side, I minus B D inverse 0 and I, and we can basically simplify this equation on the left hand side. This is what it's going to look like. We obtain that the derivative of the camera pose is going to look like this in terms of the error in the camera pose and error in the world point X. And same thing for the derivative in the world point X is going to be of this form. And the trick for us is to figure out a way to do this really quick. Remember that when we have a block diagram matrix, we can trivially invert it this particular way by inverting each of the diagonal elements. And since D is basically a diagonal matrix in this case, this becomes really quick. And remember that A minus BD inverse B transpose is the Schur complement of D, which makes it super efficient for us because this Schur complement part is a small sized matrix, which is of the size of the camera pose into camera pose. So which is like 1000 by 1000 or so rather than a million by million. So we save orders of factor of magnitude by doing this trick, and we can actually be able to do this real time on a robot. Right? This is the trick that really gets us to do real time. Just to quickly recap, when we started this entire journey, we wanted to find the Jacobian of the camera pose and the world point, so to see how they affect the error. But we found out that this Jacobian matrix, when you have the camera point and the world points, it's huge. It could be something like million by million dimensional, and we can't really do this. So what we can do instead is we see that J is a sparse matrix, and when we do the update rule, we want to do J transpose J. And as we start simplifying this together, we see that J transpose J has a structure which looks like a Schur complement part. And because the Schur complement of the diagonal matrix D, which is for the points, which is the larger part of the matrix, is a small size matrix, we can get away by inverting it this particular way. And that's what enables us to do this entire operation in real time. You might be wondering, do I have to implement all this stuff for myself? Do I really have to go ahead and do this? The answer is not really. Since we know that J is sparse, we know that J transpose J is sparse, we want to minimize the geometric error, and the geometric error looks this way. The optimization problem is basically minimizing this like reprojection error, and we add a little term here called the visibility matrix V. This visibility matrix is what is used for sparsity, which says, okay, does this link exist? It's a non-zero element, or is this a zero element, right? So when you use something like SciPy optimized least squares or PySBA, for example, it has a special parameter or a flag for sparsity, right? And if you go to this sort of link, that sort of helps you get around this. And just by implementing a flag and implementing this visibility matrix V, you can essentially utilize this entire thing in a very simple way. To obtain the visibility matrix is fairly simple. You would apply the chirality constraint and see which of these camera pose sees which of the world points. And if there is a constraint, you will basically put a 1 there. If not, you will put a 0 and you get away with it, right? So remember that like when we were doing the PNP and we did like linear to nonlinear PNP, there was a big decrease in error. We essentially want to do this equivalent for like multiple frames together with the world points, right? You can utilize something called the visibility matrix to implement this and this matrix V into the linear least squares SBA or PySBA. So the way we are going to do that is we essentially want to say which camera view sees which point, and it's fairly simple to do this. In this particular case, we have obtained like 3 different cameras and 4 different points. Each of the cameras sees all the points, so this is what Jacobian is going to look like. And in the first case, basically like you see that like we are only talking about camera 1 to 0.1 Jacobian, so everything else is 0, and basically these are going to be 1s, and so on and so forth. And these are 2 values per row. So what we essentially did was we took a bunch of images, either could be from a self-driving car or basically could be a handheld camera for architectural purposes. And we essentially like did a lot of stuff, and then at the end we said, okay, we have a bunch of points, we have a bunch of camera poses, twiddle around all of them so that the error is minimized the best case, right? So before the bundle adjustment, you see these blue points, and after the bundle adjustment, you see these red points. So one thing I want you to observe is this is the top view of the building on the left hand side. The red points are a lot crisper and sharper, and the walls are almost perfectly 90 degrees. But in the case of the blue one, they were like warped and curved, and that's what we want to look at. And the camera poses with the numbers are shown on the bottom as triangles. Congratulations, you just estimated camera poses and world locations using a bunch of images from a monocular camera. This is called structure from motion in computer vision or simultaneous localization and mapping in robotics. The only subtle difference is that in structure from motion, the order of images is random and it's unordered pair of images, and they can be from different cameras and so on and so forth. In SLAM, it's generally from the same camera and it's a temporal sequence. Just to quickly recap, why do we need bundle adjustment? Why is bundle adjustment called so? Why is bundle adjustment so computationally expensive? What can we do to make bundle adjustment faster, and what is the trick we have done? See you next time. Take care. Bye-bye.